Hi everyone. In this video, we're going to discuss mainly about the Neyman-Pearson lemma. So before moving on to what is Neyman-Pearson lemma, we shall see what is a test and what is a best test. So our basic question is what is a best test or which is the best test among the tests that we can give. So the first and foremost thing is an any hypothesis, and that hypothesis or the null hypothesis denoted by H naught. So, if we have any hypothesis H naught, then we may suggest a number of tests. So, the question is among these number of tests that we are going to suggest, which is the best one? So, this question is not a recent one, it had been discussed in the history, and in 1930s two British statisticians J. Neyman and E.S. Pearson studied this problem and developed an approach which has gained so much of importance and so much of use. So, this approach, which was studied by Neyman and Pearson, was of universal acceptance. So, according to them, the best test is that for which the significance level is less than a pre assigned value alpha and that test that has the maximum power. So, a best test is a test for which the significance level is less than alpha and power is maximum. So, we know what is a best test. So, we have another name for this best test, that is the most powerful test. So, for the most powerful test, we have to do something. Or to find the most powerful test, we have some steps. So, the first thing is we have to fix the significance level. That is, we have to fix a value alpha. That is usually taken to be 0.05 or 0.01. If it is not specified, you usually take alpha to be 0.05. And we only consider those tests for which the significance level is less than this alpha. Now we have a number of tests who satisfies this second condition, that is those tests for which the significance level is less than alpha. So among these tests for which the significance level is less than alpha, we have to find the test which has the maximum power. So for all those tests, we calculate the power and we choose those tests or we choose that test which has the maximum power. So such a test is called the best test, and we call that best test as the most powerful test of the given size or of the given significance level. So this is how the most powerful test is chosen. Now, if the hypothesis that we have to test, that is null hypothesis, and the alternative hypothesis are both simple hypotheses, then Neyman and Pearson have suggested a method for finding out the best test or the most powerful test for testing this problem. So, if the alternative and the simple and the null are both simple, then Neyman and Pearson have suggested a method and which is discussed in the Neyman-Pearson lemma. So, we know we always take a decision based on a random sample, isn't it? Yes. So, first of all, for the Neyman-Pearson lemma, the statement of Neyman-Pearson lemma, we have to choose a random sample. So the statement is as follows. Let x1, x2, etc. xn be a random sample from a population with a particular PDF f of x theta. So since x1, x2, etc. are a random sample, we can say that x1, x2, etc. xn are IID, that is independent and identically distributed. Why? Because it is a random sample. Now the next thing what we do in a testing problem is to find the critical region. So we define the critical region as C, where let C be a subset of a sample space such that for each point belonging to C, we have the test statistic value less than or equal to K. That means when our test statistic, that is L of x1, x2, etc. xn given h0 divided by L of x1, x2, etc. xn divided by, given h1 is less than or equal to K, then we reject h0. That is, then for each point belonging to C or each point belonging to the rejection region, we will have this function as less than or equal to K. And similarly, for each point of the sample space not belonging to C, we will have this function greater than or equal to K. Here, L of x1, x2, etc. xn under H is a likelihood function or likelihood function of the sample when the hypothesis H is true. So in the numerator, it is H0 is true, that is the null hypothesis is true, and in the denominator, we have the alternative hypothesis as true. Now, since our H0 and H1, that is the null hypothesis and the alternative hypothesis, are both simple, everything in this distribution is known. That is, L of x1, x2, etc. xn given h0 doesn't have any unknown parameters. Also, L of x1, x2, etc. xn under h1 also does not have any unknown parameters. Why? Because h0 in h0 we know the value of that parameter, and in h1 we know the value of the parameter. So this is another value for the parameter. So here what is unknown is the constant k. So we take a decision depending on the value k, because if that test statistic value is less than or equal to k, we reject h0, and if it is greater than or equal to k, we accept h0. Now we move on to the determination of this k, and this k is determined such that probability of type 1 error is alpha. So what is probability of type 1 error? Probability of type 1 error is probability of rejecting h0 when h0 is true. So when do we reject h0? We reject h0 when this sample x1, x2, etc. xn belongs to the critical region. So whenever this x1, x2, etc. xn belongs to the critical region, then we reject h0. So we determine k when probability of x1, x2, etc. xn belongs to this critical region under h0, that is when h0 is true, which is taken to be alpha. So this is a Neyman-Pearson lemma defined for a simple hypothesis, simple null hypothesis against a simple alternative. Thank you.